Hello everyone and welcome. Hello and welcome. It is a pleasure to teach you all today over video. We are going to talk about 4.4, which is a section about vector equation of a line and 3D vectors. So we are going to start with a warm-up on projections. Next problem in the warm-up will be on parametric equations. And then we are going to introduce equations of lines as vector equations. And then finally we will look into how vectors and projections can be generalized into 3 dimensions. So give the warm-up a try and then have a look at the solutions, please. So in problem 1, we are asked to find the angle formed by vectors 5, -6 and -2, -7. So what we are going to use here is the idea of a scalar product or dot product. So I'm going to start by finding dot product of those two vectors. That's 5 times -2 is -10, plus -6 times -7 is plus 42. And then divide that by the product of their magnitudes. Take an inverse cosine and you will find that the angle between the vectors is about 55.75 degrees. For the second problem, we were asked to find the scalar projection of 8, 2 onto 1, -5. Reminder, scalar projection or comp of u onto v can be found as dot product of the two vectors divided by the magnitude of the vector we project onto. So I'm going to do the dot product. 8 times 1 is 8 plus 2 times -5. That makes -2 altogether. That's the dot product. And now I divide by the magnitude of the vector onto which we are projecting. That's magnitude of this vector, 1 plus -5 squared. That's square root of 26 for the magnitude. And then finally for problem 3, we are asked to find vector projection. So we expect vector to be the answer. And we are projecting 4, -3 onto 6, 2. So then we derived this formula last time in class. Here are two different ways how this formula can be written. It relies on having the vector v, which is the direction of the projection, multiplied by, and now this is the dot product over the magnitude of v squared. So my vector v onto which I'm projecting was 6, 2. And now I'm going to evaluate this part of the expression. Dot product of u and v is 24 minus 6, so that's 18. And magnitude of the vector v onto which we are projecting is 36 plus 4, that's 40. Magnitude would be with a square root, but the magnitude is squared, so that's 18 over 40 altogether. Simplify this vector by performing the scalar times vector operation, leaves us with 2.7 and 0.9 for components of this vector. Problem 4 of today's warm-up will require you to have either a graphing calculator or Desmos on hand. So if you are in a classroom, go grab yourselves and Inspire. So we are working with a baseball. Baseball is hit 2 feet from the ground at the speed of 120 feet per second, while the wind is blowing 10 feet per second straight across the field from home plate to the outfield wall. So that's in the direction of the motion of the baseball. What we will do with this velocity or speed, we will add that to the baseball's horizontal velocity. There's a wall 400 feet from home plate that is 20 feet high. The ball hits exactly the top of the wall, and we are interested in knowing at what angle was the ball hit. So what was the initial angle under which the baseball started this motion? So, couple of reminders. We talked about projectile motion using parametric equations before. So here are the horizontal and vertical distance traveled in terms of time. V0 is the initial velocity, theta is the angle under which the ball was hit. That's what we are trying to figure out. Vertical distance or height is also affected by negative 16, which is half of acceleration due to gravity downward, and then the initial height that we have given here, 2 feet. Reminder from physics, if you think about velocity, the way it relates to acceleration is using this formula where velocity is the initial velocity plus acceleration times time. So the way we are going to use this is separately in the x and y direction. So the x direction is just that, velocity multiplied by cosine of theta, just because that is the side in a triangle that would represent the motion that's adjacent. On the other hand, for the vertical velocity, we will find that as v0 sine theta, subtract 32t, which is my acceleration times time. Give this problem a try. Keep in mind that the equation you will get will be a quadratic equation into which we will need to plug in an expression for time, so you will need Desmos or graphing calculator to solve for the angle. And here are the initial ideas. So, if I was to represent the motion graphically, here is the initial velocity. The x component of that velocity is 120, so the initial velocity multiplied by cosine theta. The vertical one is 120 sine theta. My angle would be the angle under which the ball was hit. And now I can start by using the formulas for the velocity as well as the displacement to figure out at what time would the wall that is 400 feet away from home plate and 20 feet high, at what point is the wall hit. So my velocity in the x direction based on this equation would be simply the initial velocity multiplied by cosine theta, but because we also have the wind blowing with the velocity of 10 feet per second in the direction of the motion, we have an extra plus 10 over here. And now 400 was the distance, horizontal distance from the wall. So I'm going to plug that into the equation for x. So I'm getting horizontal distance 400 is the velocity, which is now 120 cosine theta plus 10 multiplied by the time. So I can express time as 400 over 120 cosine theta plus 10. So this is the time at which the ball hits the top of the wall. Now to figure out the angle at which the ball was hit, I'm also going to use the 20 feet, which is the vertical distance. So the 20 feet of vertical distance over here, which is my y, also needs to match this equation for the height of the ball. So here is me plugging in the v0 sine theta t. This is my v0 multiplied by the time that we evaluated earlier. Subtract 16t squared. That's this term. Again, I can plug in for time, what I already figured out. Add extra initial velocity, so that's the plus 2, equals to 20. So if I wanted to, I could represent that as a single function by simply saying, oh, I am going to subtract the 20, and so all this part together will be minus 18 in my function, and then my goal will be to find zeros of that function. So we are going to look into how to do that on a graphing calculator. So go get your Inspire. And now here is my graphing calculator simulator. So if I start by confirming that I want to graph, now this is my blank graph, and I'm going to graph the function to find the angle, which are the zeros of the function. So I'm going to go to Menu, Graph Entry and Edit. I'm going to enter the function. And now you would just be typing in the function. I prepared that ahead of time. So here is the entire function typed in. Note how it ends with minus 18. That is for the plus 2 minus 20. So I'm going to graph that function. And what I'm seeing right now is a graph that doesn't have particularly convenient window for me to look for the zeros. I see that the zeros would be somewhere here and there, but I want to zoom in a little bit. So what I'm going to do is go to Menu, Window Zoom, Window Settings, and for my x value, well, time wouldn't be negative, so I do not really need to go that far. I'm just going to leave some space to see the entire positive half axis. X maximum, there on the graph, it looked like maybe 100 would do. Minimum for y, since we are looking for zeros, I do not need to go too deep. And then again on that graph, when we saw it in the unspecific window, it kind of looked like 100 would do. Confirm. And what I see right now is zoomed in part of the function, and these are my zeros. So to identify the zeros on the TI Inspire, I would go to Menu, Analyze Graph, and the very first item is a 0. What the calculator asks you to do is to find a lower bound and upper bound for your zeros, and we will find 1 0 at a time. So here I'm going to click left and right of what appears to be a 0, and it just found me coordinates of 1 point. So the first time will be about 31 seconds. And I'm going to do that again. Menu, Analyze Graph 0, click left, click right of the 0 point. Here is the other one. It looks kind of funny that the y coordinate isn't actually 0, but you see it's a decimal raised to the power of 10 to negative 11, so very close to 0. It evaluates things numerically, and the time is about 65.3 seconds. 31 and 65.3 is what you get approximately for the angle in degrees. So here it is even more accurately. I believe I evaluated those on Desmos. That's why those answers are more accurate than what the graphing calculator showed me. All right, so that was the baseball problem. Next, we are going to look into here are the instructions for the Inspire if you wanted to see them in writing. If that's better than the demonstration, I will also put the Desmos link with the equation and the graph into the description of this video. Next, we are going to practice some sketching of projections just to practice what we learned last time. So we have vectors G and F. The vectors are of 3 different kinds, and for each G and F you are asked to both sketch the vector projection but also estimate what would be the scalar projection of each when we project G onto F. To give you an idea of scale, this is the standard unit vector J, 0, 1, and so you should use this for reference to guesstimate what would be the components of the scalar projection. Give that a try and then come back for the solutions. So here are the pictures. Keep in mind that if we are doing projection of G onto F, we are casting shadow of G on F, so the projection has the same direction as F, or opposite in case of negative scalar projection. So here is my projection using this for scale as 1. Approximately 0.2, 1.8 would be the components of that projection. Plus or minus 1 or 2/10 of a unit would be perfectly fine. We are just learning to interpret the images, so accuracy isn't the greatest goal here. For this position of vectors, when the angle between them is obtuse, when I cast shadow of G onto F perpendicularly, it actually happens to be the case that the vector projection would be pointing opposite to the vector F. So the components of the vector projection would be roughly 1.2 and negative 0.5. And then when I have G and F perpendicular, projecting G onto F gives me a single point or you could interpret that as a zero vector with component 0, 0. All right, now we are going to start thinking about equations of lines. So equations of lines, the way we know them, work with slope. We are going to learn today how to write vector equations and look how that relates to writing parametric equations of lines in 2 dimensions. So as we know from algebra, if I was to just find equation of line that passes through 2 given points, what I could do is simply find the slope, rise over run, which turns out to be 7 over 10. Note that this line is increasing, hence the slope is positive. And now I can choose one of the forms of equations of lines, such as slope point form. So here, either of the points would do. I subtract y coordinate from y, subtract x coordinate from x, and this is the slope of my line. So now, how could we use vectors to represent this line? Initial idea to represent this line using vectors might be to start from the origin and represent each point on that line with its own vector. Sadly, that's very unfortunate because that type of representation wouldn't really bear information about the slope or the direction of the line. So instead, we are going to just have one vector that goes from the origin to a certain point on the line. It can actually be any point on that line whatsoever. And then the remaining part of that vector equation will represent the direction or slope of the actual line. So this is how that would look like. xy as a vector equation would be in the form -2, 4, which is the vector going from the origin to one of the points on the line, such as -2, 4. And then I will use t as a parameter and multiply that by the direction vector of that line. And the direction vector of that line is simply the vector going from -2, 4 to 8, 11, which is a vector with x component 10 and y component 7. Now we are going to do some practice on vector equations as well as parametric equations and think about how they relate to each other. So have a look at those questions, please give them a try, and then we are going to look at the solutions. Note that many of them have multiple or even infinitely many solutions when you are writing the vector equations. So question 1 asked you about line that contains the points 1, 4, and 6, 7. So part A, we are going to write a vector equation of that line. So the way we are going to do it, vector equation has vector xy on one side, and then on the other side, as my initial vector, I can use any vector from the origin to a point on that line, such as the 1, 4 itself. And then the direction of the line is represented by this directional vector, which is going from 1, 4 to 6, 7. So that's vector 5, 3 multiplied by the parameter t. Couple things to notice is that if I plug in t is 0, I will just get 1, 4, which tells you, yay, 0.14 is indeed on that line because there exists a value of t for which we receive 1, 4 from this equation. If I plug in t equals to 1, I will get 1 plus 5 is 6, 4 plus 3 is 7. So that tells you that this equation, this vector equation, truly represents a line that passes through the 2 given points. In part B, we are asked to write a parametric equation of the line. So a way to do that is to use t as a parameter and write 2 separate equations, one for x and one for y. And I can use my vector equation to do just that by breaking it into components. So x equals 1 plus 5t, y equals 4 plus 3t is an example of a parametric equation of the line. If I was to find the point that is halfway between those two, that is just the midpoint. I could find the average of them. 1 plus 6 over 2 is 3.5. 4 plus 7, that quantity over 2 is 5.5. But I can also use the way I set up my parametric equation, where I got 1, 4 for t is 0, and 6, 7 for t is 1. So if I plug in 1/2, I will get exactly halfway through between these 2 points. So that's 1 plus 5 over 2, and 4 plus 3 over 2, which makes my 3.5 and 5.5. In part D, we are asked to find the point that is 5/6 on the way from 1, 4 to 6, 7. I can use the same idea and plug in 5/6 for time t and evaluate what that equals to. In question 2, we will ask to find the vector equation of the line y equals to 2x plus 5. Notice that this 2 represents the slope of that line. So for rise 2, we get run 1. So the way I can write this equation is choose any point on that line. For example, that could be my y-intercept, 0, 5. And then write the vector equation as xy as a vector equals to now vector from the origin to the chosen point on that line, that's the 0, 5, plus parameter t times the directional vector of that line, and that is 1, 2, because if I was to think about how the slope works in this case, the slope was rise 2 for run 1. So this as a vector would be the vector 1, 2. All right, in question 3, we are asked to write another vector equation, so find another representation of that same line, such as both vectors in my equation are different from the original ones. So again, for the initial vector, I can use any point on that line. So it seems like here I, for example, plugged in 1 for x. And so if I do that, I get y is 7. So 1, 7 is a point on that line that I can use as an initial vector. And then plus t times, that's the parameter, the directional vector. And now think about how 1, 2 and 2, 4 have the same direction. So really, when we talk about directional vectors, the magnitude doesn't matter. It's just the direction that represents the slope of that line. So here I can have any multiple of 1, 2, even negative multiple of 1, 2, that would still represent the exact same line. All right, and now here's the good news. So everything we learned so far about 2D vectors and projections can also be generalized into 3 dimensions. So we are now going to practice that on 3-dimensional vectors, x, y, z. U will have components 1, negative 5, 3. V will have components negative 3, negative 2, 2. And it is your job to practice some operations. This notation with the roof is the unit vector. In this case, since it's u with the roof, it's unit vector that has the same direction as vector u, sorry. We will also find the angle between vectors, apply the same formula with the dot product. It just has 3 dimensions now. J, we've seen before, that's the standard unit vector in y direction. The new standard unit vector is k, that is the standard unit vector in the z direction. You will also find the dot product, find the scalar projection of u onto v, and find 2 vector projections, v onto u and v onto v. Here is the reminder of the formulas. They don't change at all in 3 dimensions. You just have extra z component to think about. Give the questions a try and then have a look at the solutions. So in question A, we are asked to do 2u plus v. That is simply working component by component with the addition. 1 plus negative 3 makes negative 2u. 2 plus negative 3 makes negative 1. Negative 10 plus negative 2 makes negative 12. 6 plus 2 makes 8. Then in part B, we were asked to find the unit vector in the direction of u. So I'm going to start by finding the magnitude of u by square rooting sum of the squares of each component. That gives me root of 35. And now to find the unit vector in direction of u, I will take what u was originally, 1, negative 5, 3, and divide each component by the magnitude of u, so that gives me this unit vector. For part C, I'm going to need a dot product, so I will actually do part E first. The dot product is simply multiplying the x coordinates together, the y components together, the z components together, and add them all up. So 1 times negative 3 is negative 3. Negative 5 times negative 2 is plus 10. So far I have 7. Plus 3 times 2 is 6. 7 plus 6 makes 13. Then back to C. To find the angle between the vectors u and v, I'm going to take an inverse cosine of the dot product, which is the 13, divided by the product of the magnitudes of the individual vectors. And if I ask calculator to help me with the inverse cosine, I will get an angle of about 57.8 degrees. In part D, we will ask to perform a calculation with standard unit vectors. So J was 0, 1 in 2 dimensions. Now it's 0, 1, 0 in 3 dimensions. K is the standard unit vector in the z direction. So that would be 0, 0, 1, 0, 0, 5 when I do the 5K. So now I'm going to component by component evaluate the vector. So if I did z, for example, this has component 0, minus 5k is minus 5, minus another 6, that's negative 11 altogether. We already did E, so next up we have the projections. So reminder, scalar projection should lead to a number, but vector projections should give me a vector. So in part F, I am doing scalar projection of u onto v. So that's me taking dot product of the two vectors, that gives me 13, dividing by the magnitude of the vector onto which I'm projecting, and that's the vector v. 9 plus 4 makes 17, so that's square root of 17. If I do a vector projection of v onto u, I need to switch the formula around a little bit accordingly. So it's going to be in the u direction, and then u is multiplied by the stretch or shrink factor that is very similar to the scalar over here, but there is an extra magnitude of the vector we are projecting onto. So we talked about how dot product is commutative because I can switch the vectors around and get the same answer. So v times u is still 13. Magnitude of u we found before, that was root of 35. Now I have that squared, so just 35. And this is the vector u, so I could multiply this vector by this scalar to simplify this further. And now finally, if I do projection of v onto v, that's casting shadow of v onto v. So that's v itself, so that would just be the vector negative 3, negative 2, 2. But you could also use the formula and evaluate the vector that way. A lot of things would cancel and you would just be left with the vector v alone. All right, here is some more practice in 3 dimensions. This time we are looking at 2 points and we will use those points to refer back to some vectors and figure out some relationships. So if I have point A with coordinates 3, negative 6, 2, and point B with coordinates 4, 1, negative 3, we are asked to do 8 different things, including vector equation and parametric equation, as well as finding an equation of the sphere with center A passing through B. So give this question a try, and then we are going to go over the solutions. So finding vector AB, that is a vector that starts at A and ends at B. So sometimes people just remember to do B minus A. You can also ask yourselves the question, what would you have to add or subtract to get from 3 to 4? That would be plus 1. So the coordinates of AB are 1, 7, negative 5, and the magnitude is 1 plus 49 plus 25, that's root of 75. In part 2, we are asked to find the scalar projection of the vector AB onto 1, 0, 1. So here we are going to be using the same equations that we've learned before. Reminder, the equation for scalar projection is just dot product divided by magnitude of the vector we project onto. So here, if I was to do that, dot product of 1, 0, 1 and 1, 7, negative 5 is the 1 plus 0 minus 5, that's the negative 4. And then I'm projecting onto 101, which has a magnitude of square root of 2. In part 3, we are asked to find vector projection of the vector AB onto 101 again. Oh, this time it's vector. Got it. So for vector projection, we are going to take the direction we desire, which is the 101, and now multiply that by, remembering the formulas, multiplying that by dot product over magnitude of the vector we are projecting onto squared. So here is dot product again, negative 4, and then magnitude of the vector we are projecting onto is a 2. In part 4, we are asked to find the midpoint of the segment AB. So we could just find the average. 3 plus 4, the quantity divided by 2 would be 7 over 2, that's 3.5. We will also later test this idea by plugging a value into the parametric representation or vector representation, either way. In 5, we are looking for vector equation of the line AB. So one way how I can do that is directly use point A as my initial vector. Notice how now the vector equation has x, y, z. I am also adding the parameter multiplied by the directional vector of the line. So that's the vector AB 1, 7, negative 5. And now since the way this is set up is that if I plug in t is 0, I get 3, negative 6, 2. And if I plug in t is 1, I get 4, 1, negative 3. Halfway through is the midpoint. So plugging in 1/2 for t should give me the midpoint again. So I will test that out, for example, on the y component or y coordinate. Minus 6 plus half times 7 is minus 6 plus 3.5, and that's negative 2.5. To find the parametric equation of the line AB, I can just rewrite it, the vector equation, into parametric form. So that's me looking at one component at a time, and I have 3 equations to represent the line parametrically. And then 7, find the point that is 2/3 of the way from A to B. I can just use either the vector equation or the parametric equation, plug in 2/3 for t to evaluate what would be the coordinates. And then finally, last question of the day is looking for a sphere with center A that passes through B. So we touched onto spheres when we did quadratic surfaces because, believe it or not, sphere is just a special ellipsoid. So to set up the center at A, I will have x minus 3, y plus 6 as z minus 2. Each of those expressions is squared. All those squares are positive. And then I just need to make sure this sphere passes through point B. So I will plug in 4, 1, negative 3 into the left-hand side to find out what should my right-hand side be. So if I plug in 4 here, I'm getting 1 plus 7 squared, so that's 50 so far, plus another 5 squared, that's 25, that's 75. So this is an equation of a sphere with center A passing through B. That's all. Thank you very much for watching, and see you soon.